Let us look at the taxa which are commonly used in biostratigraphy. This is not an exhaustive list, but to give a basic idea. It is interesting to note that no single group of organisms fulfills all the criteria for the ideal zone fossils, and it is very difficult to say that fossil X can serve purpose for a very long range of time. By the way, in that case it is no more a zone fossil. We are expecting as zone fossil several of the species at different shorter time intervals to work. Now, there are certain fossils such as graptolites which have been used widely in Ordovician and Silurian ages rocks, and there are other fossils which are restricted to certain phases or particular succession. Let us start with the marine fossils. The hard parts of invertebrates are common in sedimentary rocks. These hard parts, also known as tests, and they are usually calcareous, and they are found throughout the Phanerozoic. And based on these hard parts, system, series and stages are defined. Soft parts are very rarely preserved, and in most of the biostratigraphic correlation, the hard parts of the dead organisms are considered. What are easy to identify are the different mollusks, arthropods and echinoderms, and a field geologist can easily identify them and can divide the geological time scale. The microfossils are taxa that leave fossil remains that are too small to be clearly seen with naked eyes or with hand lens. However, they are very important in biostratigraphy because they preserve very well. Being small portion, they do not get usually broken, and the entire body can be seen under a microscope. Sometimes we use a scanning electron microscope for detailed morphological analysis. The three groups that are used in biostratigraphy mainly are the foraminifers or forams, radiolaria and calcareous algae. Now, this calcareous algae includes nanofossils also. The other microfossils are that of ostracod, diatom and conodonts. Let us look at the marine microfossils starting with trilobites. These are the Paleozoic arthropods, and they are used essentially to do the zonation of the Cambrian. That is important. Cambrian zonation can be done using trilobites. Now, they are extinct. We do not see in the present world any of the trilobites. Most of these trilobites are of the benthic forms, and they stayed in shallow marine waters. They evolved very rapidly into taxa with distinct and recognizable characteristics, but they are only locally abundant as fossils. Even if we are looking at the very old rock, even if we are looking at the Cambrian rocks, not everywhere they can be found. Let us look at the graptolites. These are somewhat enigmatic organisms. They stay in colonies and skeletal structures may be present. They probably had a planktonic habit, and they were widespread in Ordovician and Silurian, very important, whereas trilobites exclusive in Cambrian, in Ordovician and Silurian, the graptolites are prevalent, and they are found in the mud rocks, in fine grained sedimentary rocks. We will not find them in coarse grained sedimentary rocks such as conglomerates. They preserve normally as a thin film or flattened organic material into the bedding plane of fine grained sedimentary rocks such as the mudstones, shales. And if you look at this figure, it has teeth like appearance, and that is being said here. They have the teeth like appearance. They can be examined with hand lens. Sometimes they are visible and sometimes under an optical microscope. They also underwent very rapid evolution, and that has allowed a high resolution biostratigraphy in the Ordovician and Silurian system. The problem is that their preservation potential is poor in coarser grained rocks such as the sandstones, and in conglomerates it becomes literally impossible. Let us look at the brachiopods. Here only one figure is given, but there can be ranges of figures of different species of brachiopods, of trilobites, of graptolites, etc. Brachiopods, shelly sessile organisms, generally make poor zone fossils. They are generally poor zone fossils if I compare the usefulness of graptolites and trilobites, but in shallow marine high energy environment where graptolites were not preserved, brachiopods are used for regional correlation purpose in Silurian rock and in late Paleozoic strata. I am asking the students to make a list of the fossil that I am describing and the age where they are used as the markers. Do it for trilobites, they are for the Cambrian. For graptolites, they are done for the Ordovician and Silurian. Then write down here brachiopods, and write down that for the Silurian rocks they can be useful, and in the late Paleozoic strata also they are used. In high energy environment, the graptolites are not preserved and their brachiopods can be preserved. So, there it has been used. So, in high energy environment of Silurian rock, where which one is expected to be used as the index fossil, graptolites or certain brachiopods? The answer is brachiopod. And in low energy environment, which one of the Silurian age will be useful? The answer is the graptolites. Let us look at the ammonoids. This is basically the taxonomic group of the cephalopods, and they belongs to the phylum Mollusca. The more familiar is the ammonites of the Mesozoic, and ammonites are used in Mesozoic correlation. In the Kutch basin in India, the ammonites are used as the zone fossil. We do have the existing living group, and the nautiloids are the most close related living groups at present. The large size and free swimming habit of these cephalopods made them an excellent group for biostratigraphic purpose. Ammonoids can swim freely, therefore they are spread over a wide range, and their large size enables easy identification. So, they can be useful, so they are useful in biostratigraphic correlation. They are found in different fully marine environments and they are relatively robust. The suture lines of the ammonoids kept changing with time, and that has been used also in correlating the rocks. The ammonoids became extinct at the end of Cretaceous. That means at the KT boundary, ammonoids became extinct. KT boundary, ammonoids got, this is also the time when the dinosaurs got extinct, and large impact of meteorite also happened on the earth most probably. Let us look at the gastropods. These also belong to the Mollusca. We said earlier ammonoids belong to the Mollusca, and the marine snails are abundant as fossils in the Cenozoic rocks. We can also find examples of garden snails where this kind of geometry can be seen, where the species is much more elongated than this width. If this is parameter A and here is parameter B, then A divided by B is more than the figure which is shown here. The gastropods are found in almost all shallow marine environments. The ornaments within the calcareous shells, the ornaments developed on these parts become very important to distinguish the different taxa within this group. Let us look at the echinoderms. This phylum includes the crinoids, sea lilies, and echinoids, also known as sea urchins. Most crinoids probably lived attached to substrata, and this sessile characteristic make them rather poor zone fossils. Whereas ammonoids were free swimming and they had a widespread, echinoderms were having a sessile character. For that reason, they are poor zone fossils. They are found abundant in some Paleozoic limestone. Echinoids are benthic, whereas the crinoids are sessile. Echinoids are benthic, living on soft sediment, and their relative robust form and subtle but distinct changes in their morphology have made them useful for regional and worldwide correlation parts of the Cretaceous. So, if I compare between the crinoid and echinoids, which one is more useful in correlation? The answer is echinoid, because they are more widely spread and worldwide correlation in parts of Cretaceous. Remember, it is not in any other portions where the echinoids have been used significantly. Now, let us look at the corals. Abundant corals have been found in the shallow marine limestones in the Devonian and in the lower Carboniferous ages. These two ages to remember where the corals are most dominant. In the form of reef they occur, so that to withstand the rough water of the sea in the shallow depth. However, note that they are generally not suitable for biostratigraphic purpose because they have a very restricted depositional environments where they occur. Let us look at the foraminifera, in short is also known as forum. Forums have been studied very extensively, therefore, an entire branch of micropaleontology exists that is known as the foraminiferology. These are the single-celled marine organisms that belong to the protozoa subkingdom. They have been found as fossil in strata as old as the Cambrian. This is the time when we had the trilobites, and they also have been found in the present day world. But they have different species that appeared and then that got disappeared at different time ranges. Therefore, even though foraminifera is found right from Cambrian, they are very extensively used in biostratigraphic correlation. Foraminiferology is fundamental in hydrocarbon industries or in hydrocarbon geoscience. The calcareous forams usually became more abundant through the Phanerozoic and in many Mesozoic and Cenozoic marine strata. What is the size of the tests, test, calcareous tests of the planktonic foram? They are typically a millimeter or less than that. So, less than equal to 1 millimeter. So, naturally we need optical microscope to study them, whereas there are a few of them which are more than a centimeter in diameter. Now, those which are having more than 1 centimeter in diameter can be identified with a hand lens. The planktonic forams evolved rapidly and they are found in the marine strata. Forams are readily recoverable from the boreholes, and therefore, as I was telling you, they have been used very widely in biostratigraphic correlation. Let us look at the radiolaria. Radiolaria forms a subclass of the planktonic protozoans. They are found in the deep marine strata. Note this term. Regarding radiolaria, we are saying that they are found in the deep marine strata. We did not make any such specific statement regarding the forams. Radiolaria commonly have the silica skeletons, whereas in case of foraminifera we said that they have the calcareous tests. The tests chemistry of foraminifera and the skeleton chemistry of radiolaria are markedly different. Radiolarian appearance is nearly spherical, often with spines. So, these are the spines, and these organisms are again less than 1 millimeter in diameter. They are important to date the deep marine deposits because the skeleton survives in the siliceous ooze deposited at depth below the CCD, carbonate compensation depth. Radiolarian chart is a common appearance. Within chart we may get radiolaria. High resolution biozonation schemes have worked for the radiolaria for the deep sea sediments. Radiolaria have been used to work on the Paleozoic strata more extensively. So, if a question comes where the radiolaria fossils get maximum use in biostratigraphy, is it the Mesozoic, is it the Paleozoic, or is it the Cenozoic? The answer can be the Paleozoic strata. Let us look at the calcareous nanofossil. As the name indicates, the test is calcareous, just like that of for foraminifera, but you can see the difference. It is spherical, whereas subspherical geometry is not sufficient to describe the foraminiferal test. In case of calcareous nanofossil also, again they cannot be seen with the naked eye. High power optical microscopes are required to study them. They are microns to tens of microns across, and that is why the word nano has been used. The most common nanofossils are the coccoliths. Coccoliths can be the constituents of some fine grained limestones such as the chalk of the upper Cretaceous. They are found above the CCD. Why? Because this is calcareous, so there has to be above the carbonate compensation depth. They have been used biostratigraphy in Mesozoic and the Cenozoic strata, whereas the calcareous nanofossils have been extensively used to do biostratigraphic correlation for the Mesozoic and Cenozoic strata. The radiolaria has been used most extensively to do the biostratigraphic studies on the Paleozoic strata. Let us look at the ostracods. These are small crustaceans having two valve calcareous carapace, and they are closely relative of the crabs and the lobsters. Their deposition, the deposition environment where they stay is very wide. They can stay both in freshwater and in marine environment. They have a long history. Since they are found both in freshwater and in the marine condition, both in marine and non-marine environments, zonations have been performed using the ostracods. Let us look at diatoms briefly. These are a kind of algae with siliceous frustule or skeleton. So, this is siliceous. So, one similarity between the radiolaria and diatom is that they are both made up of siliceous materials. Diatoms are found both in shallow marine and in freshwater setting. The frustule is less than 1 millimeter, that means this is a microfossil, and that is what was the heading. We are looking at the microfossils here. They can also be found in the lacustrine environment, and they are rarely used in biostratigraphy. Rarely does not mean never used, but their use is restricted. Let us look at the conodonts. They are tooth-like structures. This word tooth-like was also seen when we were describing graptolites. So, graptolites and conodonts have tooth-like appearances. Conodonts occur in the Paleozoic strata. Even though we do not know the origin from where they are coming, they are useful stratigraphic microfossils, and it is used in case the other microfossils are rare in the rock. Let us look at the acritarchs. These are microscopic spiny structures. A similarity between acritarchs and radiolaria exists, but they are distinct. In case of radiolaria, we have a spherical body and then there are spines. In case of acritarchs, there is an overall geometry of subspherical appearance and then there are spines. One can easily see the kind of the spine here and the kind of the spine here are different. The acritarchs are found in the Proterozoic and in the Paleozoic rocks. Acritarchs have been used in the Precambrian strata for biostratigraphic purpose. Acritarchs have been used in the Tethyan sediments of Indian Himalaya. In this list, we started with foraminifera. Why did we start with foraminifera? Because foraminifera is most widely used in biostratigraphic correlation when we are looking at the microfossils. That is why we started the discussion of marine microfossils with foraminifera and not with any other taxa. Just like the marine fossils, we also have the terrestrial fossil groups that are used in biostratigraphy. Here is a brief discussion. Note that in the continental environment, fossils are less likely to be preserved. That is what is said. Poor preservation potential exists here in the subaerial setting. Certain vertebrate teeth can be preserved, and these teeth are made up of organophosphates and some bones that can be preserved. Pollens, spores and seeds, collectively called palynomorphs. Palynomorphs include the pollens, spores and seeds. These get preserved, and the palynomorphs are in fact the most common materials in the terrestrial environment that are used in biostratigraphy. Here are a few examples of the palynomorphs: plant pollen, seeds and spores. Their sizes are very small, it can be of micron level, so high power microscopes are required to study them. The palynomorphs can resist chemical attack. They can be dissolved out using hydrofluoric acid. Airborne particles such as pollen, spores and some seeds may be widely dispersed, and the occurrence of these aeolian palynomorphs within marine strata allows for good correlation. Even though the strata can be marine, palynomorphs can get deposited there, and therefore the marine strata can also be used even with the fossils having origin in the terrestrial realm. The point is, using the palynomorphs we can do a gross correlation. High resolution correlation which is done with the marine fossils such as with forams is not possible with the spores and pollens and other palynomorphs.